I was part of the research team for a project that was based at one of the research facilities here in South Africa, which is called Ithemba Labs. And my task as a researcher in that institution was to assess the environmental impact that might be caused by the project that they had at the time. So as a research institution, Ithemba Labs, they were trying to advance their research facilities, which one of the facilities or the proposed facilities was called the Low Energy Radioactive Ion Beam, the LERIB project. And in that project, the idea was to advance their nuclear research for the purpose of nuclear physics, for the purpose of nuclear medicine, for the purpose of other nuclear-related aspects. And in the quest or in ensuring or implementing such a project, then there was a question in as far as the environment is concerned, because one can remember or understand that when we speak of nuclear, there's a likelihood for it, when it interacts with any matter at which it traverses, it's likely that it can result to, it can make the matter at which it interacts with to be radioactive. And therefore now, there was a question of the environment. It becomes easy sometimes to contain radioactivity when it comes to other ionizing radiation, but when it comes to neutron activation, neutrons in nature, they are neutral, and therefore, unlike the other ionizing radiation, it becomes difficult to contain such radioactivity. So hence there was a need to ensure as to what measures can be put in place if the neutrons can escape the facility and interact with the soil and groundwater from which this LERIB facility will be placed. So we were trying to investigate the possibility, firstly, of the neutrons to interact or to activate the soil material and the water material in the subsurface. So the key thing here, like I've said, is the environment, which is the aquifer, and the people that are living down gradient. So those are the questions that we were asking. Firstly, to check if there will be any interaction between the neutrons and the subsurface. If there is an interaction, then what is the likelihood of such activated matter to migrate from one point to another point? So to do that, there was a simulation that was run by one of the researchers at the facility, and it was discovered that at the level of 2 to 3 meters below the surface, there is a likelihood that the neutrons that might be escaping from this LERIB facility can interact at that level. And then that's when we started to do the investigation. And what I did, we had to firstly to collect the soil samples, collect the groundwater samples, and then we had to drill 6 boreholes on site at different levels. 3 of them were 40 meters below the ground, and then 3 of them were 15 meters below the ground. The idea was to check between the confined and the unconfined aquifer to assess the water quality and the soil characteristics between these 2 levels, which is your confined and your unconfined aquifer. So we took samples, and then we had to analyze the chemical composition of the soil and then the chemical composition of the water between these 6 boreholes that are drilled in different levels. From the chemistry, of course, then we had to look for your sodium, your magnesium, and a number of other chemical compositions that were in the samples. And then from there, what we had to do is we also took the same soil samples, and then we had to bombard them with the neutrons on site, right? So we had to activate these soil samples. We already understood by the chemistry what was existing, and therefore we can assume that some of the elements that were analyzed, those elements are likely to be activated, but fortunately the results showed otherwise, because it was not like all the elements that were detected by chemistry that the same when we had to take the same soil samples and activate them with neutrons were activated. we had to activate these, or to irradiate these soil samples and the water samples, right, with neutrons, so that we can have an understanding if in future, or when the LERIP facility is in operation, which stable isotopes within these elements are likely to be activated. And then from there, it was discovered that the magnesium, sodium 22, isotope of sodium 22, sodium 24, manganese 54, manganese 52, and scandium 46 were some of the elements in soil that were activated when we exposed them with neutrons. So now we had an idea that, which means the soil that we had at Ithemba Labs, if it can be activated with matter, then which amongst the elements or the isotopes that are in the soil are likely to be activated, right? So the ones that I've just listed here are the isotopes that were activated when we exposed them, or when we bombarded them with the neutrons, right? And then now the second question was, if then, what is the half-life of each of these? Because that's what becomes important as well. Because when it comes to isotopes, some of them, they can exist for very few seconds. Some of them can exist for hours. Some of them can exist for days. Some of them can exist for millions of years, right? So now, then it becomes like, if, for example, an isotope will only be formulated and have a half-life of 30 seconds, then why should you then worry about the impacts of the people that are living down gradient 30 kilometers down? Because when it reaches there, or when that same groundwater reaches that distance already, there, it's likely that the isotope would have died off of its radioactivity, or the concentration would die off. So that was the question. So among the isotopes that I've just listed now, it was only sodium 24 that was also existing in the groundwater. So some were existing in your soil samples, and then sodium 24 was the only isotope that was existing in your groundwater. The half-life for sodium 24, it is 15 hours. Now, we had to conclude, or to recommend, that the institution will have to consider at least to thicken up the concrete material, which already it's existing to some of its facilities. But now thickening the concrete material will make less or lower chances for the neutrons to escape the containment, right, the shielding. Again, another aspect was to look into the half-life, of course. The fact that where the facility is located, there's very few areas that are currently existing. Not to neglect the fact that in the future there can be areas or developed or settlement that can be in the nearby. So that factor had to be also be considered, and so therefore, hence now thickening the concrete material for shielding made it easy to just say then these neutrons will therefore not even interact with the soil and groundwater. Because remember, outside the obligation of the people that are living down gradient, then according to section 24 of the Constitution, we also have the obligation to ensure that the environment, the natural environment itself, it is protected from any possibilities of pollution or possibilities of contamination. So therefore that had to be considered as well. So hence thickening the concrete material had to be considered, or was the best choice in terms of ensuring that the neutrons will not penetrate to a point that they activate your groundwater and your soil material at your subsurface. So that is the project in a nutshell.